This is video number 2 for sections 11.4 and 11.5, equations of hyperbolas. We have one last non-function to meet, and that is what is called a hyperbola. And about the best way I can describe it for you is what I have written down here. A hyperbola is a two-part graph that is asymptotic at both ends, meaning there are asymptotes at all the ends. I'll show you a couple of simple drawings. Now again, to keep things as simple as possible, we're only going to consider two types: horizontal hyperbolas and vertical hyperbolas. We're also only going to consider hyperbolas that are centered at 0, 0. Let me draw for you a horizontal hyperbola along with its asymptotes. The dashed blue lines are the asymptotes. There are two of them. Remember, an asymptote is a line that a graph gets really close to but never quite touches. The solid blue shape is the hyperbola. This is one hyperbola. It does come in two pieces, but it is one hyperbola. Two-part graph, asymptotic at both ends. You can also have a vertical hyperbola, which is the same idea, except the two pieces go up and down instead of side to side. These shapes may remind you of parabolas, and I know they are somewhat similar looking, but they are not parabolas. Parabolas are not asymptotic, meaning parabolas just keep getting wider and wider and wider. There's no line that the parabola starts to look like. But with hyperbolas, at the end of the graph, you almost can't tell the difference between the graph and the straight line. Just like for ellipses, I've given you the general equation of a hyperbola. Actually, I should say equations. There are two. There is one version for a horizontal hyperbola and one version for a vertical hyperbola. If you compare back to the ellipse equation, you will see it is exactly the same thing except for the minus sign in the middle. The ellipse had a plus, otherwise it was identical. Of course, the order matters with subtraction, and that's why there is this second version over here. This is the one where the y comes first and the x comes second. If the x is first, you'll have a horizontal hyperbola. If the y is first, you will have a vertical hyperbola. Again, just like for ellipses, if we can figure out what the A and B do, then we'll be able to quickly sketch a graph. These are a little bit more complicated, but still, once you see the pattern, you can actually get the graph up pretty quickly. Here's a sample problem that we'll look at. Just from first glance, I can tell this is going to be a vertical hyperbola because the y comes first. Some of the things that we need to investigate are the x and y intercepts, as well as the asymptotes. If you can get the intercepts and asymptotes, you can draw these pictures pretty quickly. Okay, intercepts, that's going to be similar to what we did in the ellipse example. I'll start with x-intercepts. We always find x-intercepts the same way, by filling in y as 0. We saw some of this same math in the last video. The 0 part basically disappears. Then I'm going to have to clear the fractions. And actually, while I'm at it, why don't I multiply both sides by -9? That'll take care of that negative over there as well. That's going to give me positive x squared equals -9. And then I'll use the square root method, square root, plus or minus. And this is where I have trouble because I can't do the square root of -9. So apparently that means there aren't any x-intercepts. Well, look, that's not shocking. Look back up at the picture. We already knew this was a vertical hyperbola. Vertical hyperbolas do not touch the x-axis. These solid pieces are nowhere near the x-axis. So this makes sense. There aren't going to be any x-intercepts when you have a vertical hyperbola. There will be for a horizontal, but not for a vertical. Okay, am I expecting y-intercepts? Well, I am. Vertical hyperbolas definitely have y-intercepts. How would I find that for this example? Just like before, fill in 0 in place of the x. Now this part zeroes out. If I clear the fractions, I think this time we're going to get an answer here. I have y squared equals 4, square root, plus or minus, and I get y equals plus or minus 2. So there are two y-intercepts, positive 2 and negative 2. You're probably already looking for patterns. It's the same simple pattern we found with the ellipses. Why did these come out to be 2? Because the b, the number sitting, or rather the square root of the number sitting underneath the y part, is 2. It's the same result we had before. If there are y-intercepts, they will be plus or minus b. And similarly, if there are x-intercepts, they will be plus or minus a. Okay, so that's pretty simple. It's the asymptotes that are going to require a little bit more investigation here. Remember, asymptotes are lines that the graph gets really, really close to when x gets very, very large, either on the positive side or on the negative side. So keep that in mind. That's what I'm trying to investigate. In order to show you this, let me take my example equation, and I would like to solve this equation for y. I would like to isolate the y. Well, let's see. I can move that x term over to the other side, and then I can multiply through by 4, giving me y squared on the left, 4/9 x squared plus 4 on the right. And then if I square root both sides, don't forget the plus or minus, then I have isolated the y. Now, here's what I want you to think about. If you were to plug in a really large x, 1,000, 1,000,000, something like that, what would you do? First, you would square it. That would result in even a much larger number. Then you would multiply it by 4/9. That's close to a half, but still, if you cut one of those really ridiculously large numbers, 1,000,000, 1,000,000,000, 1,000,000,000,000 in half, you still have a ridiculously large number. Then you would add 4 to it. That 4, very negligible. I mean, imagine somebody giving you $1,000,000 and saying, or I could give you $1,000,000 and 4. You wouldn't really care about the 4 at that point. It's not doing much of anything. When x gets large, this 4 is kind of irrelevant. If you ignore the 4, watch what happens to this equation. This now becomes just plus or minus the square root of 4/9 x squared. Well, everything in that square root is a perfect square. I can simplify that to just y equals plus or minus 2/3 x. 2/3 times 2/3 is 4/9. X times x is x squared. Look at this. These are lines. These are y equals mx plus b's. So you know what we just figured out? We figured out the asymptotes. When the x gets really, really large, we're saying the hyperbola will be almost the same thing as these two lines, these two asymptotes. Well, I really have everything I need now to graph this hyperbola. What I will do is I will draw on the asymptotes first. This is always going to be very quick and easy. You can see there's no plus b on the end of these things, right? For y equals mx plus b. That means the y-intercept every time is going to be at 0, 0. And then just think about the slope. One of the asymptotes has a slope of positive 2/3. That would be go up 2 and right 3 and connect the dots. And then the other one has a slope of negative 2/3. So go down 2 and then right 3. I'm just thinking in terms of rise over run, and connect those dots for the second asymptote. Then mark on the two y-intercepts we found, 2 and negative 2. And finally, just fill in that vertical hyperbola. Now, we don't want to have to do all this work every time, so we want to now look for some patterns and generalize. We've already stated the patterns for the x and y intercepts. If the x-intercepts are going to exist, which they would in a horizontal hyperbola, they are going to exist at plus or minus the a. If you have a vertical hyperbola, on the other hand, and you have y-intercepts, then those are going to exist at plus or minus b. What about the asymptotes? Well, hopefully you have already realized that they fit a very, very, very simple pattern as well. You're not going to have to go all through this again. Why did it come out to be a 2 on the top and a 3 on the bottom here? Because those are the a and b numbers. In particular, the 2 is the b. The square root of the number underneath the y part is the b. And the a is the 3. The square root of the number under the x part is the a. So what we're saying is every single time the asymptotes are always going to be plus or minus b over a x. In this case, it was 2 over 3 because that was the b over a. You don't really even have to memorize that. All I really ever remember is that the b tells me the rise part of the asymptote, and the a tells me the run part of the asymptote. You don't really need the whole equations. You just need to know the rise and the run. In fact, let me show you perhaps a more speedy way of getting those asymptotes. All you have to do is this. When you first see your hyperbola, jot down for yourself the values of a and b. A is the square root of the number underneath the x. B, the square root of the number underneath the y. Just remember the y number tells you the up and down part, and the x number, the a, tells you the side to side part. All I do is I start at 0, 0, and in all 4 directions I go vertically 2 and horizontally 3. So that means up 2 and right 3, up 2 and left 3, down 2 and right 3, down 2 and left 3. If you just then connect those dots diagonally, you've got your asymptotes. That's all it is. It works every time. Some people even like to draw in a little rectangle connecting these 4 dots. And then you know that the asymptotes are simply the lines that go diagonally through the rectangle. Now just put back on your intercepts. Remember we had y-intercepts at 2 as well as at -2. And draw in your hyperbola and you're done. I'll work a fresh example problem for you in the next video.